Hi all. Last day we have seen two important permutation groups, S3 that is also same as D3, symmetries of an equilateral triangle, and the other thing was D4. D4 is the fourth dihedral subgroup, dihedral group, and denoted by Dn. So Sn and Dn are two important groups consisting of permutations. Okay, anyway, this Dn is always a subgroup of Sn. So this is subgroup of Sn. So yesterday we have discussed S3 and D4. Okay, and this D4 is also called octic group. So please note this name. This is in fact the symmetries of group of symmetries of square, group of symmetries of square, and this groups has some these groups have some interesting subgroups. So S3 we have discussed S3 as the rho naught, rho 1, rho 2, and mu1, mu2, mu3. So these are the elements of S3. And if you consider or if you observe the group table that we have discussed the last class, we can get some subgroups of this S3 as obviously trivial subgroup is also there. So this is the trivial subgroup consisting of this identity element. And if we collect rho naught, rho 1, rho 2, those are the rotations that forms a subgroups of S3 as well. Okay, so similarly you can get another subgroups as rho naught mu1. This will be a subgroup, and another subgroup is rho naught mu2 and rho naught mu1, mu3. This is because we know that every element of S3 generates subgroups of S3. So this rho naught generates the subgroup generated by rho naught is rho naught itself, and similarly you can consider the subgroups generated by each of these elements. Okay, when you observe the subgroup generated by rho 1 and rho 2, that will be same. Okay, those subgroups will be the same as this rho naught, rho 1, rho 2, since this rho 2 is the inverse of rho 1 that you have discussed in the last class. And if you observe the subgroup generated by mu1, so that will give rho naught and mu1. As this rho naught is an identity element of S3, that element comes in all the subgroups. So the subgroup generated by mu1 is this one. Subgroup generated by mu2 consists of mu2 and rho naught and mu2, and subgroup generated by mu3 is mu3 and rho naught. Okay, so these are the subgroups of S3. So once you collect all the subgroups of S3, you can arrange it in a hierarchy. If we write the subgroups, trivial subgroup in the last level, and if since these subgroups have two elements each, so we can place it in the next higher level. So we write this as the subgroups here: subgroup generated by mu1 and subgroup generated by mu2 and subgroup generated by mu3. Okay, these are the subgroups with two elements. And come to the next subgroup, that is this one, subgroup generated by rho 1 or subgroup generated by rho 2, that consists of three permutations. So that can be placed in the next level. That is either you can write that is subgroup generated by rho 1 or subgroup generated by rho 2. Finally, the subgroup is improper subgroup, that is S3 itself. Okay, so once you collect all the subgroups of a group and place it in different levels according to their number of elements, and you can connect all these subgroups using an arrow mark. So I put an arrow mark like this. This means that this rho naught, the subgroup in the lower level is a subgroup of the next higher level. Okay, so this is the singleton set rho naught is a subgroup of mu1. Similarly, singleton set rho naught is a subgroup of mu2 as well, and mu3. And we know that subgroup generated by rho1 contains this as the trivial subgroup, and all these subgroups are subgroups of S3. So we never connect this singleton rho naught to S3, because these are all we need to collect only the consecutive levels. We are not connecting or joining these two things, S3 and rho naught, because that is not in the consecutive level. Okay, so once you place all the subgroups in this manner, it's called the subgroup diagram. Okay, this is the subgroup diagram. Okay, sometimes this is called a Hesse diagram. Okay, so similarly, as an exercise, you can do the you can draw the Hesse diagram for, or subgroup diagram for D4. So D4 has some interesting subgroups, and collect all the subgroups of D4 and try to draw the subgroup diagram for D4. Next we have a definition. Let f from A to B be a function and H is a subgroup of this A. Now you define the image of H under F. Okay, then that is denoted by this f of H. So f of H consists of all f of H for H belongs to H. Okay, that means this is the image set. You might have heard about this definition earlier, and so please remember this one. And next we will prove the theorem, or not theorem, lemma to prove a famous theorem called Cayleys theorem. So this is the lemma for Cayleys theorem. This theorem states that, this lemma states that, the statement of lemma is let G and G prime be groups, and phi from G to G prime be a one-to-one function such that phi of xy equal to phi of x into phi of y for all x comma y belongs to G. In fact, this is the definition of the homomorphism. So we will study homomorphism later on. Then phi of G, so this is the symbol for image set. So this is the square bracket, not the symbol bracket or parenthesis. So this is phi of G, denotes the image set of this G under phi. This is a subgroup of G prime. So that is the theorem, that is the lemma. Phi of G is a subgroup of G prime, and phi provides an isomorphism of G with phi of G. So that is trivial, because if we are since we are considering this one homomorphism, and the only thing remains to show that this is to be an isomorphism is ontoness. If we are considering phi of G, then this is an image set, hence that is always onto map, so that will give an isomorphism. Okay, so first we prove this phi of capital G is a subgroup. Okay, is a subgroup of G prime. So this is how this is what we have to prove. So first we have to observe the closure property of this phi of G under phi. So phi of G under the binary operation of G prime. So we start with two arbitrary element x prime and y prime of phi of G. Since these are elements of phi of G, there should exist x comma y belongs to G such that x prime is equal to phi of x and y prime is equal to phi of y. Now if we consider x prime, y prime, so that will be phi of x, phi of y. Using the definition, you can write this is phi of xy, so that is same as, that is an element of phi of capital G, because this x prime, y prime is an image of some element of G, that's the thing. So this proves the closure property. So next we will prove the existence of identity. We know that since G prime is a group, then E prime exists in G prime. We need to prove that E prime is also an element of this phi of capital G. Okay, so we start with this E prime times phi of E. Phi of E is always an element of phi of G because this E is an element of G. So this can be written as, we know that this is same as phi of E because E prime is the identity element. But this is phi of E times E, that is equal to phi of E into phi of E. Okay, so by right cancellation law, we can get E prime is equal to phi of E. So this is always an element of phi of capital G because that is the image of identity element of G. So this proves the existence of identity element. Next we will prove the existence of the inverses. So if we choose any x prime belongs to this phi of G, then we will prove that x prime inverse is also in this. Okay, so that is because since this x prime is an element of this, you can write x prime as is equal to phi of x for some x. Okay, then you can write E prime is equal to, we know that E prime is phi of E, that we have proved here itself. So E prime can be written as phi of E, but E can be written as x inverse. Okay, for this x is an element of G, then x inverse is also an element of G, then x inverse will give the identity, therefore identity can be replaced by this. Now using the property of this phi, it's a homomorphism, so this can be written as phi of x into phi of x inverse. Okay, but what is phi of x? Phi of x equal to x prime, so this is x prime times phi of x inverse, which shows that E prime can be obtained by multiplying these two. Okay, so this proves that inverse of this element is this one. Okay, so x prime inverse is equal to phi of x inverse. Okay, so that means inverse of this, obviously this is an element of phi of capital G because x inverse is also an element of G. So this shows that inverse of x prime is also an element of this phi of G. Okay, so this proves that phi of G is a group. Okay, it's a, in fact it is a subgroup of G prime. This proves the lemma. Using that lemma, we can prove theorem 8.16, Cayleys theorem. So before we going to establish this theorem, we recall some groups. In order to illustrate that the next theorem, I recall our famous group Z3 under addition modulo 3. Okay, we know that this consists of the elements 0, 1, 2 along with the addition modulo 3. So this form a group, and as all we know, the group table 0, 1, 2, 0, 1, 2, these are the group tables. This is the way we construct the group tables of Zn. So here we have 0, 1, 2, this is 1, this is 2, and we know that 1 plus 1 is 2 and 1 plus 2 is 3. So if you are using the addition modulo 3, we can get the remainder as 0, and 2 plus 1 is also 0. 2 plus 2 is equal to 4. So when we divide that 4 by 3, you can get the remainder as 1. So this form the group table for Z3. Okay, so the next theorem says that this group has a representation of group consisting of permutations. Okay, that means there should exist a permutation group. That means there should exist a group consisting of some permutations which is isomorphic to this. Okay, or you can rename this 0, 1, 2, all these elements of this group can be replaced by permutations. Okay, and that form a group of permutation. Okay, that is not the same as Zn, but a group consisting of that is not same as the Sn, but that there exists a group consisting of some permutations corresponding to this. Okay, so that is the thing we have to prove in the next theorem. Every group can be made isomorphic to a group of permutation. Okay, so how will you prove that theorem? So I'll illustrate that theorem using this group Z3, this typical group Z3. So in order to get find out that those permutations, we fix an element of this group. Okay, so I'll fix 1 itself. 1 belongs to Z3. We know that if you take any arbitrary element from this Z3, so without loss of generality, I take 1 here. 1 belongs to Z3. We know 1 belongs to Z3. So we construct, using this 1, we construct elements, permutations corresponding to each of these elements. Okay, so how will you construct element corresponding to permutation corresponding to 1, not corresponding to 0? If you take 1, then you can construct a permutation corresponding to this 1. Okay, so how will you construct that? So in order to construct the permutation, we use these 3 symbols rather than 1 2 3. We write 0 1 2. We already discussed that the symbols are irrelevant. You can choose any 3 symbols. So without loss of generality, I take 0 1 2 here, and using this 1, I operate this 1 on each of these elements. So that is 1 plus 1 addition modulo 3 0, so that will give 1, and 1 addition modulo 1, so that is 2, and 1 addition modulo 2, that is 3, that is remainder is 0. Okay, so when you operate this one with these elements, you will get the corresponding images, and we will make those elements are the images of the corresponding elements. Okay, so if you take 0, then what is the permutation corresponding to 0? So we write 0 1 2 here, and operate the 0 with these elements, so you will get the same thing. Okay, and if you have 2, then what is the element corresponding to 2? So that is 0 1 2 here, then we operate 2 with the 0, so that will be 2, and 2 addition modulo 3 1, that is 0, because that is 3, and 2 plus 2, that is 1 here. So these are the 3 elements. I call these elements as lambda 1, and this is lambda 0, and this is lambda 2. That means the permutation corresponding to 1, and permutation corresponding to 0, and permutation corresponding to 2. Okay, once you obtain these 3 elements, we can construct a new group consisting of these elements, lambda naught, lambda 1, and lambda 2. Okay, and we operate the elements of this. How will you construct the table? So I call this as some the permutation group. The corresponding the group corresponds to this Z3. So we write it as S Z3. That's the permutation corresponding to the elements of Z3. So how will you? What are the binary operation here? Okay, we operate. We define lambda 1. These are permutation anyway. So we can define composition in this permutation. So lambda composition, lambda 1 composition, lambda 2, and so this is in fact lambda 1 composition, lambda 2. How will you work? Okay, so that is 0 1 2, lambda 1 is 1 2 0, and what is lambda 2? Lambda 2 is this one, 0 1 2 2 0 1, and when you take the product here, you can get 0 1 2 as here 0 goes to 2 and 2 goes to 0, and here 1 goes to 0, 0 goes to 1, and 2 goes to 1, and 1 goes to 2. Okay, so this will give lambda naught, lambda 0. Okay, so in the similar fashion, you can define or this form a group with respect to composition. So these are elements are lambda naught, lambda 1, lambda 2, lambda naught, lambda 1, lambda 2, and with respect to permutation, multiplication, or composition, this is a group. You can easily get this is lambda naught, lambda 1, lambda 2, this is lambda 1, lambda 2, and when you operate lambda 1 and lambda 1, you can get lambda 2, lambda 1 and lambda 2, you can get lambda naught, and this is lambda naught. Again you can perform these multiplication and you can observe that these are the elements. Okay, so this is lambda 1. Okay, now you can get a group table corresponding to this. Okay, once you construct permutations using the elements of Z3, and those permutations make a group with respect to composition, permutation composition. So when you consider this correspondence, when you change this to 1 goes to this, 0 goes to this, and 2 goes to this, and this these two groups are isomorphic. Okay, that means there is a 1 1 on 2 homomorphism from this group to this. In fact, that mapping is nothing but this one. Okay, this is the way we prove the next theorem. If you can replace this Z3 by any group, any arbitrary group, or any finite or infinite group. For each group, if you fix a group first G, then corresponding to each element of that group, we will construct permutations. Okay, using this idea. Okay, so how will you define this permutation? This permutation, if this is lambda 1, what then how will you get lambda 1 of 0? Lambda 1 of 0 is nothing but 1 plus 0. Okay, how will you get lambda 1 of 1? This is 1 addition modulo 3 1. Okay, and how will you get lambda 1 of 2? That is 1 addition modulo 3 2. That means operate 1 from the left hand side of each of these elements. Okay, so this defines a map. Similarly, how will you get lambda naught? What is lambda naught of 0? That is 0 addition modulo 3 0. Lambda naught of 1 is obtained by operating 0 from the left hand side of this 1. Okay, so lambda 1 of lambda 0 of 2 will be 0 addition modulo 3 2. Okay, so this is the definition of. So in general, if you fix an element x belongs to Z3, how will you construct the permutation corresponding to this x? Okay, so if that is the if that permutation is lambda x, then how will you evaluate lambda x of that G? Okay, in order to get this lambda x of G, you operate this x from the left hand side of this G, or you can operate the same x with right hand side, then that will give another set of permutation or another representation for this. Okay, so once you represent Z3 using this group, then this consists of permutations. Okay, this is what the next theorem asserts, theorem 8.16 theorem. This theorem is a famous named theorem called Cayleys theorem. Cayleys theorem. This theorem states that every group is isomorphic to a group of permutations. Okay, that means if we start with an arbitrary group G, so to prove this, we start with an arbitrary group, G be a group, then we construct SG, okay, or not SG, the subgroup of SG. So we already discussed what is SG consisting of. So I'll make this this is a subset of, okay, so this is subset of Z3 here. So this is the symbol what we have used here. SG consists of set of all functions f from G to G such that f is a permutation, or f is a 1 1 on 2 map. Okay, or permutation, this is also called permutations. Okay, so we will construct a subgroup of this. Okay, so first we in order to define that subgroup, we define lambda x first. Define lambda x. What is lambda x? Lambda x is a function from G to G such that lambda x of G is equal to xg for all G belongs to G. Okay, so this is the permutation correspond. This is a 1 1 on 2 function, so you can easily verify that this is 1 1 on 2. Lambda x of G1 equal to lambda x of G2 will give this is xg1 equal to x g2. By left cancellation law you can get g1 equal to g2. So this shows that this lambda x is a 1 function. And similarly, if you take any g belongs to g, then you can get implies x inverse g is also an element of g, because x is an element of g. This implies we know that, but we know that what is lambda x of this x inverse g? That is x times x inverse g, that will give g, which shows that for any g belongs to g, there exists an element x inverse g belongs to g whose image is this one. So which shows that this is onto. So from this you can say that lambda x is a bijection, okay, bijection or a permutation. So this defines a permutation corresponding to x. So each x belongs to g, there exists a permutation. Okay, so which so this would enable us to define a subgroup of this SG. So I collect all the lambda x such that x belongs to g. Okay, so this is always a subgroup of, or we will prove that this is always a subset of SG, and we will prove that this is a subgroup. Okay, so how will you prove this is subgroup? So first of all, we have to evaluate the closure property. So we choose two elements, lambda x comma lambda y belongs to the subgroup, the subset. Then I call this the textbook, there is I think there is no name for this set, so I put it as some capital X. Okay, so if this lambda x lambda y belongs to x, then what is lambda x composition lambda y? So in order to evaluate lambda x composition lambda y, we have to evaluate lambda x composition lambda y of g. Okay, so this is lambda x of yg by definition, and this is xyg, and this can be considered as lambda xy of g, which shows that lambda x lambda y, okay, lambda x lambda y is nothing but lambda xy. Okay, so this is also an element of x. Yeah, now this proves the closure property, and next we will prove the inverse. What is lambda? Obviously, since E belongs to G, then lambda E belongs to this X. This lambda X will give lambda X EX, or lambda X is the same as lambda X, which is equal to lambda XE, that is equal to lambda X lambda E. This shows that lambda E is the identity of this X, or that is identity permutation. And now if we have lambda x of what is lambda x inverse of g? By definition, this is x inverse of g. Okay, and similarly, what is lambda x? We will prove that this our claim is to prove this lambda x inverse equal to lambda x whole inverse. Okay, so lambda x whole inverse, that means when you compose this lambda x and lambda x inverse, lambda x composition lambda x inverse of g will give lambda x of x inverse of g. So that is equal to x inverse g, which is equal to g itself, that is lambda e of g. Okay, which shows that lambda x and lambda x inverse are inverses. Okay, therefore every lambda x belongs to this x, there is a inverse. So which shows that this x is a subgroup, not only the subset, it is a subgroup of this SG. Okay, so we will show that this x is isomorphic to G. Okay, that means we will define a new new function, or new function from x to this SG, which is 1 1 and on to homomorphism. So we define a new function mu from G to x. This is a subset or subgroup of SG. Okay, so we can avoid this one, you can directly define a function mu from G to Sg. Okay, defined by mu of this x will give mu of any x is our lambda x inverse. So this is the function. In the textbooks, I use the same symbol from the textbook. So this is the symbol. This function is denoted by phi. So I call this as phi and defined by phi of x equal to lambda x. So this is our new function. Then you can easily get this is a 1, 1, 2 function, because this phi of x equal to phi of y, that implies lambda x equal to lambda y. Okay, so lambda x equal to lambda y means these two permutations are the same. So this will be same as lambda x of e is equal to lambda y of e. Okay, that implies x e is equal to y e, that is equal to x equal to y, which proves the one-oneness of this phi. And we can easily get this is a homomorphism, because phi of x xy, that is in fact lambda xy. We already proved that lambda xy is equal to lambda x into lambda y. So this is equal to lambda phi of x into phi of y. Okay, so you need not worry about the onto-ness. We already proved the lemma that if there exists a phi from one group to G to another group Sg, which is 1, 1, such that phi of xy equal to phi of x into phi of y, then we can easily get the image set. This G or G will be isomorphic to the image set of G under this phi, which is the in this case, which is the subgroup of Sg. We already proved that image set is a subgroup, and this is in fact our x that we have discussed earlier. Okay, so this proves Cayleys theorem, and we already discussed that instead of taking once you define lambda x in this manner, lambda x of g is equal to xg. Okay, the similar fashion you can find out the permutation corresponding to x as mu x of g is equal to, you can write it as mu x of g is equal to gx. Okay, so in this fashion you can define another set of or another group representing the same g, so that these two things are called, this is what we call left representation, and this is called right regular representations. Okay, so there are two different names for these two representations. The same thing, you can retrace the same thing using this definition. Okay, so these two representations are called left regular representation and right regular representations respectively. Okay, so this with this we can conclude section 8. In the next class we will discuss section 9 onwards.